Back in 1997, our sensors tracked a patch of Indonesian swamp exhaling more carbon in 3 months than all of Europe emits in a year. We missed it. The models failed. Then, in 2015, the telemetry showed it happening again. 3 continents failing at once through completely different mechanisms. Now, NOAA is projecting a 2026 super El Niño that could dwarf them both. This is the data point that should haunt you. The forests in the path are more fragile than we have ever seen them. This is not just a weather report from orbit. It is a study of the primary system keeping this planet habitable. Can it survive? Follow our data here at the Skylab. We are in the early stages. The surge hasn't peaked yet. Forest telemetry is still streaming in, and the more we see, the more alarming it gets. Stay with me for the next data drop. Let us begin. Part 1. The forecast that quietly breached a planetary threshold. There is a specific value hidden in a government database that almost nobody outside our circle of atmospheric scientists is monitoring. If you truly grasped what this reading implies, you would find it much harder to sleep soundly tonight. The number is 2.75, 2.75 degrees. That is the extreme edge of the ensemble forecast for the Niño 3.4 region in the Central Pacific. It serves as the thermostat for our entire biosphere. NOAA sees a 61% chance this region hits the super threshold. This isn't a minor spike, it is a super event, a massive anomaly we have only recorded twice, in 97 and 15. Every time this happens, the headlines are predictable. Flooding in Peru, scorched earth in Australia, and smoke clouds choking cities. You have seen these images before. Most of the media ecosystem covers the climate through this same narrow lens. The reporting isn't incorrect. These disasters are real, they are catastrophic, and they deserve every minute of airtime they receive. But here is what the headlines miss. The deeper story hiding beneath the surface, invisible to most but glaring on our sensors. It is far more critical than the nightly news. Every year, our civilization pumps 40 gigatons of carbon dioxide into the atmosphere. A gigaton is 1 billion metric tons. That scale is nearly impossible to visualize. So look at it this way. Imagine every vehicle, aircraft and factory on Earth running at full capacity, 24 hours a day, all year long. That is the magnitude of our output. Yet, remarkably, only about half of that carbon remains in the air. The rest, nearly 20 gigatons annually, is scrubbed away. Not by our machines, but by the oceans and living biological systems. The tropical belts of the Amazon and Southeast Asia act as the largest terrestrial carbon sinks on the planet. They inhale carbon dioxide like planetary lungs, locking it into the soil. Below them, the oceans use chemistry to do the same. Together, they form an invisible infrastructure, a biological backstop that has quietly absorbed half of our waste for decades. Without this safety net, atmospheric carbon concentrations would be climbing twice as fast as the rates we currently observe. Without it, our climate projections would look far more dire. Here is the mechanical detail about El Niño the media misses. A major El Niño is more than a heat shift. When that warm Pacific water moves, the entire global engine changes. It doesn't just alter rainfall patterns, it penetrates the biology of continents and places immense stress on the world's forests. It desiccates the peatlands, it pushes ecosystems past the point of absorption and into the danger zone of active carbon release. These extreme events can actually shut down the planet's ability to scrub carbon from the atmosphere. In 97, our sensors saw Indonesian fires dump up to 2.5 gigatons of carbon in mere months. During the 2015 event, the global sink weakened so much that carbon dioxide surged at the fastest rate ever recorded. 2.5 gigatons of excess carbon escaped that year. Eventually, the system stabilized and the forests came back online. The growth rate returned to the baseline trend, and we in the scientific community logged it as a significant, yet temporary, anomaly. But now, We are asking the question nobody wants to hear. A few researchers are hinting at it in peer-reviewed papers. The question is whether that recovery will happen again in 2026. It isn't just about the severity of the drought. It is whether this system, already damaged by decades of stress, can even reboot its carbon sink at all after this next hit. That is the real crisis. To understand the gravity of it, you and I need to look at why this cycle is different. You have to understand that the baseline health of the forests and soils that form our invisible infrastructure has fundamentally shifted. This shift makes a recovery less certain than ever. The floods and droughts will dominate the news cycle as always. But the carbon cycle is what keeps this planet habitable, and it is about to face the ultimate stress test of our era. Let us start at the beginning. We will lead with the forecast and a metric that almost nobody uses. Most people know El Niño as a temperature anomaly. We use the Oceanic Niño Index, the ONI, as the standard tool. It tracks how much the surface temperature of the Pacific deviates from a 30-year average. If our sensors register 0.5 degrees Celsius for 5 overlapping cycles, it is an El Niño. Reach 1.5 and we have a strong one. Hit 2.0 and we enter super El Niño territory. That is the metric in our scientific reports and the one screaming in the headlines. But there is a different metric that some of us are watching more closely. It tells a far more alarming story about our planet's future. We call it the Relative Oceanic Niño Index, or RONI. And the difference between the ONI and the RONI is not just technical. It is a shift in how we must interpret the data for 2026. Here is the core problem with the standard ONI measurement. Its baseline uses a 30-year rolling average that resets every decade. Essentially, our reference point for what counts as normal is being dragged upward by the heat. Since background temperatures are rising, the entire Pacific biosphere is hotter now than in the 1990s. It is warmer than even the 2000s. It is even hotter than when the 1997 event set the modern benchmark for these planetary super events. When we claim 2026 matches the anomaly of 1997, we are ignoring that the starting line has already moved significantly toward the red. The absolute temperature of the ocean's surface, the engine for evaporation and atmospheric stress, is projected to reach dangerous new heights in 2026. While the anomaly looks familiar, the RONI corrects the data by using a fixed historical baseline instead of a sliding window. Consequently, recent events look much more powerful on the RONI. The standard ONI is systematically masking the true extent of the heat we are seeing. Why does this matter for the carbon sink? Because the planetary infrastructure, the forests and soils, does not respond to our statistical anomalies. They react to absolute physical conditions. An Amazonian tree doesn't care about a 30-year average, it only feels the heat currently burning its leaves. It senses the scorching soil. It knows when it can no longer photosynthesize and must simply shut down its systems to survive the crisis. As the planetary temperature climbs, every new El Niño hits a biosphere that is already stressed, thirsty, and primed for total systemic failure. Beneath the familiar headlines lies a quiet controversy. It is a reality that our mainstream climate models have not yet fully confronted. If we compare the 2026 forecast to 1997, we are likely reassuring ourselves with a number that is dangerously misleading. We mistake relative data for reality. In truth, the absolute thermal regime the forest actually inhabits is reaching a terrifying and unprecedented peak. When the baseline shifts, every biological system responding to that environment is pushed toward a dangerous new breaking point. Part B, the multi-basin configuration. From orbit, we see that the Pacific doesn't act alone. Earth is not a machine with a single switch. It is a massive web of interconnected systems. When these nodes align in the same direction, the cascading results are far more severe. We have identified a specific configuration present in the most catastrophic planetary events of the last 150 years. This rare alignment of ocean basins amplifies drought across the tropical belts, specifically targeting the regions where our remaining rainforests still breathe. It requires a triple threat: an El Niño in the Pacific, a burning Atlantic, and a phenomenon known as a positive Indian Ocean dipole. The Western Indian Ocean overheats compared to the east. We have not seen this specific alignment clearly since the 2015 cycle. Before that, the records point back to the 1870s, the era climate historians say triggered the devastating Great Victorian Famines. That was a global disruption that claimed up to 60 million lives, a total systemic collapse on a planetary scale. Mass starvation followed synchronized droughts across 3 continents. The 1877 El Niño remains one of the most destructive events in our history. Its power did not come from magnitude alone, but from its configuration. Multiple basins and systems failing in perfect, lethal unison. Our early signals for 2026 show a pattern beginning to resemble that setup. The Atlantic is already showing abnormal thermal signatures. We see rising heat in the Indian Ocean, and layered on top is a factor that did not exist in 1877. It only became a serious scientific concern in 2015. We are watching the weakening of the Atlantic Meridional Overturning Circulation, or AMOC. This planetary conveyor belt usually pumps heat away from the tropics toward the North Atlantic. As it slows, all that thermal energy stays bottled up. The heat remains trapped in the tropical Atlantic. You and I need to ask, what does this mean for our global carbon sinks? It means the Amazon, the very lungs of our planet, is being strangled by heat coming from both the Atlantic and the Pacific. Simultaneously, the Indonesian rainforests are being caught in a thermal vice between the Pacific and the Indian Ocean. The Amazon is hit by a drought from the Pacific, while amplified drying from the Atlantic strikes at the exact same time. Indonesia is squeezed by El Niño on one side and the Indian Ocean dipole on the other. This stress is not just additive. It is multiplicative. This is a coordinated assault by multiple systems, and the target is the planet's primary carbon sink. We depend on these sinks to stay ahead of the emissions curve. This multi-basin configuration is not some minor footnote. It is the reason 2026 cannot be dismissed as a simple Pacific anomaly. We are witnessing a planetary scale event. Part C. The question everyone is missing. Let's try an exercise together. Look up 2026 El Niño on any news site. Notice how they focus only on the strength of the event and the peak temperature anomaly. They are missing the bigger picture entirely. Most reports obsess over comparisons to the past, while ignoring the absolute conditions that are actually driving this planetary shift. One night, our instruments detected a massive celestial anomaly over a quiet town. Eyewitnesses reported luminous signatures that defied every known orbital trajectory. The data confirmed it wasn't a craft, and it certainly wasn't a meteor. Official reports dismissed it as a weather balloon, but the data disagreed. For decades, the raw telemetry was buried in a classified encrypted archive. That file contained deep space captures that shattered our entire understanding of physics. Let's examine the spectral data together and uncover what was being suppressed. Some hypothesize an interstellar transmission, while others fear it was a planetary warning. Whatever that signal was, our perception of the cosmos changed forever that night. This is arguably the most critical question for our planetary life support system today. Our climate projections aren't even more alarming because we assume Earth's natural carbon sinks will continue to function as intended. We're betting on forests and oceans to scrub half our emissions. Our data accounts for some gradual degradation over time. The physics supports that expectation, but we haven't modelled a sudden, catastrophic collapse of this entire planetary filtration system in the near term. Our simulations don't account for a 2026 El Niño that damages the tropical forest carbon sink beyond its ability to recover. Look at the telemetry from 1997 and 2015. Both times the biosphere's pulse eventually stabilised and returned to normal. Following 1997, we saw the atmospheric carbon dioxide growth rate spike before descending back to the expected trend line. Around 2015, the data showed a similar pattern. The growth spike faded as rain allowed the forests to reboot their systems. We logged both events as temporary glitches, essentially stress tests that the Earth's biology managed to absorb and survive. The uncertainty regarding 2026 isn't the stress test itself, but whether the planetary hardware has accumulated too much background damage. Severe moisture loss, rising temperatures, and the slow, steady erosion of the Earth's own structural and biological integrity. The recovery our sensors anticipate might not happen with such completeness, or at all. A temporary blackout of the carbon sink is dangerous. A permanent system failure, or even a long-term one, puts us in a completely different category of planetary catastrophe. It is like a space station hull absorbing a micrometeoroid strike while healthy, versus one already riddled with unchecked structural fatigue. To understand why 2026 might be the first event that truly tests that distinction, you and I must analyse the last 2 times the system failed. Those system crashes weren't clean, and they left lasting damage. Part 1, 1997, our first major carbon shock. Prior to 1997, our theories suggested that El Niño events could potentially disrupt the planet's entire carbon cycle. El Niño triggers tropical droughts. That lack of water stresses the planetary vegetation. Wilting plants absorb less carbon dioxide, causing atmospheric levels to climb. We once viewed this as a manageable planetary perturbation. Then, our satellites detected massive fires in Borneo and Sumatra. We discovered a phenomenon that no model had accurately predicted. Peat isn't like normal planetary soil. It isn't forest floor debris or rotting leaves. It's not the normal organic material that cycles through the carbon system over years or decades. Peat is carbon stored over millennia in waterlogged conditions where dead plant material simply could not decompose or break down. It compressed into deep, ancient layers. Beneath the Asian forests, these deposits reach depths of 12 to 15 meters. This carbon has been sequestered since the last ice age. It is essentially isolated from the contemporary, active carbon cycle. Think of it as geological storage, ancient carbon the planet scrubbed from its atmosphere thousands of years ago. When the 1997 drought desiccated those lands, it didn't just cause surface fires, it ignited the ground itself. When it dries, peat burns deep beneath the surface, smouldering through compressed organic layers, much like a cigarette burns through its tobacco. These subterranean fires can actually survive an entire monsoon season. They burn for months after surface fires die, venting carbon into the atmosphere that has been locked away for centuries. Our data from 97 varies wildly, proving how little we understood this massive atmospheric event at the time. The most precise analyses put the total carbon release from those fires somewhere between 0.8 and 2.5 gigatons. That uncertainty range is immense, spanning a factor of 3. Yet even the lowest end of the estimate remains absolutely staggering. At that time, global fossil fuel emissions were holding at roughly 6.5 to 7 gigatons per year. The Indonesian fires released the equivalent of 12 to 38% of annual global fossil fuel emissions just from burning peat underground. From orbit, the haze that covered Southeast Asia back then was a sight you and I can only call extraordinary. From our sensors, we saw massive smoke plumes choking the region for months. Ground operations stalled as schools and airports shut down. Below us, the health crisis was immediate and devastating. But the carbon signature was something else entirely. Invisible to the eye, it bled across the global atmosphere. It became a planetary crisis. You and I need to understand that 1997 was never meant to happen. The water levels in those peatlands should have held firm, even against a brutal El Niño drought. That carbon was supposed to stay locked underground forever. Sequestration was meant to be permanent. We discovered a terrifying flaw in Earth's carbon system, and 1997 was only the first warning sign. Part A, 2015. a triple system failure. In those intervening years, our monitoring capabilities evolved spectacularly. Our eyes in the sky became incredibly sharp. Launching OCO2 in 2014 gave us our first high-precision map of atmospheric carbon dioxide. We could finally track carbon sources at a regional level. The 2015 El Niño hit the most scrutinized climate system ever. We watched the carbon cycle react in real time, something impossible in the 90s. The data stunned us. The OCO2 data from that event confirmed a chilling fact. The planet's land carbon sink was failing. We saw a loss of 2.5 gigatons. By 2016, carbon growth hit 3.05 parts per million. It was the highest increase ever recorded then, a record that sent shockwaves through the entire scientific community. But the total numbers weren't the real story. It was how the failure mapped across the globe. In Southeast Asia, it was a repeat of 97. Peat fires released ancient carbon back into the sky. The same ground was burning again. It was a known mechanism, a predictable disaster we had tracked before. But over the Amazon, our sensors caught something new. Drought was actually shutting down photosynthesis across the basin. The jungle was losing its ability to breathe, and it was not even on fire. Trees were sealing themselves off to survive the drought, effectively killing their own carbon absorption process. In a drought, the Amazon reverses course. Trees stop growing and start exhaling carbon dioxide instead. Without photosynthesis, the forest tips from a sink to a source. It doesn't need to burn to poison the air. It just has to stop working. Now, let's look at tropical Africa, where our sensors caught something truly bizarre. Data showed a massive carbon surge in Africa, not from fire, but from warming soil microbes exhaling gas. Heat accelerates decomposition. As the ground warms, microbes pump out carbon dioxide like a biological engine. The whole African ecosystem's metabolism sped up. It was exhaling carbon without any visible sign of trouble. 3 continents, 3 distinct failures. Fire was the culprit in Indonesia this time. In the Amazon, photosynthesis stopped. In Africa, the very soil was breathing carbon. One El Niño triggered them all through different paths. Earth's life support system failed on multiple fronts. We used to think fire was the main threat to the carbon sink during El Niño cycles. The 97 fires fit that model, but 2015 proved that fire is not the only way things fall apart. You can lose the entire sink without a single flame, just through stressed trees and warming soil. There is not just one point of failure. When the heat hits a certain threshold, everything breaks at once. Part B, the failure didn't go away. The common story about these years is dangerously incomplete. People think El Niño hits, the sink fails, and carbon levels spike. Simple, right? Then it ends, the forest recovers, and we go back to normal. But that is not the whole truth. Growth rates did drop eventually. Rains returned and the forests turned green on our monitors again. But if you look closer at the telemetry, a much more alarming pattern begins to emerge. Look at the Mauna Loa data, our gold standard for measuring the atmosphere since 1958. We see the spikes from those super El Niño events clearly. But notice what happens after they peak. It looks like recovery, but the baseline growth rate is actually climbing every single year. This trend has accelerated through the decades. A normal year now is worse than a crisis year back then. It is partly our own fossil fuel emissions, but separating our signal from the planet's heartbeat is getting harder. Now, you and I have to consider a chilling theory. Our emissions might not explain everything that is happening. We are seeing a massive planetary shift, a gradual decay in Earth's carbon scrubbing systems that isn't recovering after these cosmic scale shocks. My colleagues call this the ratchet effect. Every El Niño surge strains the biosphere. It tries to stabilise, but never quite reaches baseline. The system returns more fragile, losing its resilience and becoming prone to total failure when the next shock hits. Carbon dioxide levels on our sensors spike during these events, then dip, but they never return to their pre-disturbance concentrations. The atmospheric baseline climbs higher with every cycle, leaving the planet with less reserve capacity to buffer the next extreme thermal event. Data from the 2020 Hubau study in Nature offers chilling proof that this degradation is already happening across the Amazon. Looking at 30 years of data from across the Amazon, we've tracked a steady decline in carbon absorption starting back in the 90s. It isn't just mass mortality. The biological machinery of the surviving trees is physically slowing down. Thermal stress is choking their growth, even as drought and high-velocity winds accelerate the death of the canopy. The Amazon wasn't a net emitter yet, but the telemetry showed a dark trend. Its ability to absorb was evaporating. This is why the 2026 forecast feels so ominous. From where I sit, the planet is no longer bouncing back to normal. Every planetary disturbance leaves the biosphere thinner, more exposed, and less capable of handling the next incoming thermal shock. If that is true, then we can't predict recovery by looking at the past. We're entering uncharted territory. Part 3. The hidden pattern. Every cycle leaves deep scars. When you analyse the timing of these thermal surges, a pattern emerges, and frankly, it's terrifying to watch from this perspective. After the 1997 event, the Earth had 18 years of relative stability before the next Super El Niño in 2015. 18 years is a blink in geologic time, but long enough for scorched zones in the Amazon and Indonesia to attempt recovery. It gave the soil time to rehydrate and allowed the slow biological work of forest restoration to make some headway. The system had nearly 2 decades to recharge before the next hit. But now, we're anticipating another super event in 2026. That is only an 11-year gap. Just 11 years for scorched Indonesian peatlands to try and heal from 2 previous major fires. Only 11 years for thirsty Amazonian trees to restore internal water pressures and restart their normal carbon scrubbing processes. 11 years for African soil to stabilise, though, critically, none of these planetary systems were operating in a truly stable climate. They were battling constant background warming, relentless deforestation, and localised droughts, all while trying to recover from the last global shock. It comes down to a simple calculation: recovery time versus disturbance frequency. Every planetary ecosystem has a specific timeline required to heal from a major trauma. When a tropical forest is hit this hard, it doesn't need months to heal. It needs decades of stability to restore its function. The Indonesian carbon lost in 1997 is gone. That geological bank took thousands of years to build up. We won't see that carbon return for millennia. The recovery of our ancient forests can't keep pace with the speed of these disasters. Modelling from researchers like Wenju Kai suggests that these Super El Niño events will strike more often as the planet warms. The hot Pacific and high-energy tropics that trigger these events are precisely the atmospheric conditions we are observing from orbit right now. The events aren't just getting more intense, they're getting closer together, slamming the door on the planet's chance to heal. We have a concept for this: the intermediate disturbance hypothesis. It suggests that moderate shocks can actually strengthen a system, keeping the biological diversity in a healthy state of flux. But when the frequency and intensity redline, the opposite happens. The system loses the ability to adapt and begins to shatter. It degrades. Damage accumulates faster than the repair. You and I can think of it as exercise versus catastrophic injury. Controlled stress makes a system resilient. Constant, rapid-fire trauma without recovery time simply causes the entire mechanism to collapse. Earth's tropical carbon sink has been strained twice in 30 years. Now it's facing a harder hit, with 0 recovery time on a feverish baseline. 2026 may be the moment the recovery window officially closes. The planet's clock has run out. Part 4. The Amazon is already reaching its tipping point. In 2021, a landmark paper in Nature fundamentally shifted how we view the Amazon's role in our global atmosphere. Led by Luciana Gatti, researchers flew aircraft above the canopy, sampling the atmospheric chemistry directly from the air columns above the trees. By measuring the air going in versus the air coming out, they could tell if the forest was breathing. They were literally monitoring the planet's lungs to see if it was inhaling or exhaling. The data from the southeastern Amazon was terrifying. A huge chunk of the basin has already switched to a net carbon source. This wasn't a temporary anomaly. It's a permanent shift in the planetary machinery, and you and I are watching it happen. From my orbit, you and I can see how the southeastern Amazon has crossed the line to become a permanent carbon source. The data shows fire isn't the primary culprit, it's a broken water cycle. This biome relies on evapotranspiration to survive. Roots pull water from the soil, and leaves exhale it into the atmosphere, effectively engineering their own rainfall. The forest sustains itself, but if we lose too many trees, the cycle snaps. Moisture drops and drought stress takes hold. Trees that once sequestered carbon dioxide can barely breathe. Eventually, they fall behind their own metabolic needs. The forest is exhaling more than it inhales. With less moisture recycled, the drought deepens and the process accelerates. From my vantage point, the southeastern Amazon has crossed a threshold where this feedback loop is already in motion. Experts like Thomas Lovejoy and Carlos Nobre have warned us for years about a critical tipping point at 20% deforestation. At this stage of total loss, the moisture recycling system fails, initiating a permanent transition toward a dry, savanna-like ecosystem. Our satellite sensors show current deforestation is hovering around 17 to 20%, depending on which specific dataset we analyse. The southeastern quadrant has been hit harder than anywhere else, showing much more intense drought stress on our maps. It serves as a grim leading indicator of where the entire planetary system might be heading next. When 2026 arrives, it won't find a healthy Amazon acting as a carbon sink for the planet. One full quadrant of the largest rainforest on Earth is already exhaling more carbon into the atmosphere than it can possibly absorb. El Niño won't be the thing that flips that region. It has already flipped. Now we watch if the other three quadrants can hold. This is a fundamentally different risk profile than anything we saw in 1997 or 2015. In those past events, the Amazon was stressed from a healthy baseline. We hadn't reached regional sink failure yet. Let's look at the evidence together. This failure mode is spreading, and the Indonesian peat bomb is ticking loud. When the 1997 fires swept through Borneo and Sumatra, the global scientific community was absolutely stunned. It wasn't on our maps. These peatlands were effectively invisible in the global carbon accounting models. Their massive carbon stocks were dangerously underappreciated, and their vulnerability to fire was entirely unforeseen at this massive planetary scale. Significant international efforts were launched to fix this. Indonesia even established a dedicated peat restoration agency. International funding flowed toward re-wetting projects, aiming to block the drainage canals cut for palm oil and pulpwood plantations. We tried to raise the water table to suppress fire ignition, while enhancing our satellite monitoring and detection. The results are mixed. In a structural sense, the situation today is actually worse than in 1997. Here is the reality. The fundamental problem isn't the fires themselves, it is the systemic drainage. From the 1980s through the 2000s, massive stretches of peat forest were drained for industrial plantations. Canals lowered the water table, drying out the upper layers and turning the ground into literal fuel. Undrained peat stays saturated and safe, but once drained, even a normal dry season creates a catastrophic fire risk for the region. Despite all our restoration efforts, the vast majority of that massive drainage network remains carved into the landscape today. These re-wetting projects have only reached a small fraction of the area. The structural hydrological damage is still significant. Lowered water tables have broken the vital connection between the peat and the groundwater systems that kept it saturated. This matters because the areas that burned in the past did so after their water tables were already compromised. The rewetting that has occurred since then has been insufficient to restore natural conditions in most of these areas. On top of this damage, we can see that the peat surface itself is now physically lower. When peat burns, the carbon is lost forever. In many areas, the land has literally subsided by meters from where it once stood. Lower land makes it even harder to maintain the water table because the relationship between ground and water has shifted. Areas we could have re-wetted to full saturation back in 1997 can no longer be saved with the same relative ease today. The 2026 event will hit an Indonesian landscape that has already been burned twice and drained for decades. It is only partially re-wetted and sits on a warmer thermal baseline within a regional climate that is already rapidly shifting. The potential for ignition is not lower than it was in 1997. It is actually measurably higher. The carbon exposed by decades of drainage is now dry enough to ignite and burn. This ancient carbon is a variable you and I must consider, because our current climate projections are simply missing it. Hardly anyone was discussing the Congo Basin in 1997, though we knew the forest was immense. Back then, the data infrastructure to monitor the carbon cycle in Central Africa was essentially non-existent. We have no eyes in the sky for this, no orbital sensors, no ground telemetry, and certainly no way to track regional carbon shifts. Then, in 2017, a groundbreaking report hit the journal Nature. Simon Lewis and Greta Dargi announced a massive discovery. They had mapped the largest tropical peatland on Earth right under our noses. Hidden in the Congo Basin, this site spans 145,000 square kilometres. That is nearly the size of England, largely invisible until now. Our old climate models missed it entirely. This unmapped reservoir holds an estimated 30 billion tonnes of stored carbon. To put it simply, that equals 3 years of global fossil fuel emissions sitting in a swamp. Currently, these Congo Basin peatlands are mercifully intact. They are waterlogged, shielded from the fires we see elsewhere. Unlike Southeast Asia, these hydrological systems have not been drained or disrupted by industrial agriculture yet. They do not pose the same immediate fire risk as Indonesia. However, our data shows they are dangerously sensitive to rising temperatures. Telemetry from the OCO2 satellite during the 2015 El Niño revealed a disturbing trend across the African tropical forests. The region emitted a massive carbon anomaly caused by soil microbes waking up in the heat. It was not fire or drought, just warmer ground making microbes work faster, exhaling carbon dioxide into the atmosphere at a terrifying, accelerated rate. The Congo represents a massive blind spot for our 2026 climate projections. Frankly, we still lack the monitoring infrastructure to properly characterise the risk. This giant could stay quiet, or it could exhale a massive surge of carbon if temperatures spike. We simply do not have the data to predict which path it will take. That uncertainty is exactly what keeps us up at night. Now, let's examine part 2, the soil moisture debt of 2023. 2023 and 2024 were absolute outliers on every chart we have. Global surface temperatures shattered every previous record by a staggering and unexpected margin. That gap stunned even us. Down in the Amazon, the consequences were severe, leaving scars that the public has not even noticed yet. During 2023, the Amazon faced the worst drought in recorded history, with river levels dropping to dangerous lows. The Rio Negro near Manaus plummeted. Our records show it reached levels lower than anything seen since we started tracking. We watched as dolphins died in evaporating lakes. Whole communities were stranded, cut off from the world. The scale of this catastrophe was simply enormous. But from a carbon perspective, the real story was what happened beneath the surface, hidden in the soil. You see, soil moisture is more than just damp dirt. It is a form of ecological memory. Amazonian trees survive the dry months by drinking from deep underground reserves, using water stored from the previous rainy season to maintain their growth. Deep-rooted trees can tap into water several meters down. These reserves are supposed to build up over years and be drawn down very slowly. But when a drought is this extreme, it does not just take the surface water, it drains the deep reserves from years of rainfall. That water is the forest's only buffer. Once that deep moisture is gone, it does not just come back after one good rain. It takes years of heavy rain to refill those deep pockets. And with another drought forecast for 2026, we are running out of time. The trees are now facing a compounded moisture deficit. They are entering this new cycle already parched, meaning they will hit a point of severe stress much sooner. They stay stressed longer, accumulating permanent damage. The 2023 drought was a silent killer, claiming trees without a single flame. Weakened by thirst, these trees fell prey to beetles, fungus, and wind. We are seeing a forest lose its resilience. Our sensors show a spike in mortality rates. This translates to more rotting wood and massive amounts of carbon leaking from the soil. These dying trees are a legacy of 2023. They will still be rotting in 2026, pumping carbon into the air. As we look toward 2026, the system is not starting from a healthy or hydrated baseline. It is still reeling from the after effects of the most severe drought we have ever recorded. It is entering a new crisis, already drained and damaged by the last one. Think of it like an athlete trying to run a marathon on a broken leg. The race is lost before it even begins. The coming strain will expose deep vulnerabilities that might have stayed hidden if the system had just been given time to heal. Part 3. The acceleration of the feedback loop. This is a concept we find easy to say, but hard to truly grasp. In my field, a positive feedback loop is not a good thing. It means the system is amplifying and reinforcing itself. One shift triggers another, which feeds back to make the first shift even worse. It is a runaway train that generates its own momentum. The loop becomes self-sustaining. Our carbon cycle has several of these dangerous traps built right in. What worries us about 2026 is the possibility of several of these loops activating at the exact same time. Here is the blueprint. Higher carbon dioxide levels in the atmosphere trap more heat, which rapidly warms our global climate. This warming triggers drought across the tropics. Those parched forests stop absorbing carbon and eventually start releasing it back to us. That extra carbon accelerates the warming, which intensifies the drought, which kills more of the forest. The cycle just keeps feeding itself. For eons, this planetary feedback loop has remained stable. It is the steady baseline that allowed our species to flourish. Our biosphere is designed to absorb shocks. Forests and oceans act as planetary dampers, absorbing carbon before things spiral out of control. Earth naturally seeks equilibrium. These biological buffers are remarkably efficient, keeping the global thermostat within safe and predictable limits. But if we degrade these natural buffers, the math changes. You do not need a massive spark to start a fire if the system defences are already crippled. A tiny nudge can trigger a massive collapse once the system loses its ability to self-correct. Look at the data. Our planetary resilience is fracturing. From the scarred Amazon to the smouldering Indonesian peatlands, we are seeing the structural failure of our primary life support systems. Chronic droughts and record-breaking heat are stripping away the planet's armour. The buffering capacity we once relied on is vanishing. Now, a super El Niño is approaching like a massive celestial hammer. The sheer non-linearity of this shift is what keeps us up at night. Complex systems do not die slowly. They look stable until they hit a tipping point, then they flip into a new, hostile state in an instant. It is not a slow slide. It is a sudden, violent break into a different reality. From orbit, everything looks fine, until the moment it isn't. We often do not know we have crossed a planetary threshold until it is far too late. Our models struggle to map this chaos. We are trying to weave atmospheric physics and global ecology into one coherent, predictive picture. Processing the interactions between soil, air, and water requires immense computing power. Our current simulations are simply struggling to keep pace with reality. Official reports are useful, but they are largely based on past data. They tell us where we were, not necessarily where we are going. We are entering a regime with no precedent in the record. If the system has no historical analogue, our predictive tools are effectively flying blind. As scientists, our current mission is to break down these mechanisms and quantify every single threatening variable we find. We have to calculate the odds and identify the worst-case scenarios. Some of these signals are now flashing red on our consoles. 2026 is lighting up every alarm at once. Now look at this. The ocean's carbon uptake is failing too. It is not just the forests protecting us from runaway carbon dioxide. Our planet's massive oceans have been doing the heavy lifting for decades. The seas soak up 10 billion tons of carbon every year. That is equal to the capacity of every forest on the entire planet. Now El Niño is rewriting the rules of the sea. Usually, during La Niña or neutral phases, the deep ocean cycles in a predictable rhythm. We monitor cold, carbon-heavy water rising from the depths along the equator. It is a vital part of the Earth's natural breathing cycle. This rising water captures atmospheric heat and carbon dioxide, but it also releases ancient carbon from the deep back into the sky. This makes parts of the Pacific a natural carbon source. It is one of the few places where the ocean actually contributes to atmospheric levels. But during El Niño, a massive warm pool shifts eastward. This thermal layer acts like a lid, suppressing the deep, cold water upwelling. Less upwelling means less carbon escaping the deep sea. At first glance, you might think that would help stabilize our atmosphere. In that one region, the ocean becomes a carbon sink. But as we zoom out, the total planetary picture becomes far more alarming. As a super El Niño cooks the surface, the water's ability to hold carbon dioxide drops. Basic chemistry tells us warm liquids reject gas. Hot water simply cannot hold on to carbon dioxide. Across vast swathes of the Pacific, the ocean's absorption rate is stalling out. The exact global impact is still being debated in scientific circles. Many studies suggest that failing forests are the bigger threat, while the ocean changes are just a minor, temporary distraction from the trend. The real nightmare for 2026 is that baseline sea temperatures are hitting record highs. The data signature is off the charts. If our forests stop breathing and the oceans can no longer absorb the overflow, we lose our two biggest safety nets at once. The ocean is not some bottomless tank. It is warming, acidifying, and its efficiency as a carbon filter is rapidly approaching its limit. Losing both planetary shields simultaneously? That is a catastrophic scenario. This is where we drift into uncharted territory. Next up, agricultural fragility. This planetary system failure is not just an abstract data point. It directly threatens the fragile infrastructure we rely on for survival. The same heat and drought strangling the forests are now ripping through our global food supply. It is a cascading failure across the entire biological grid. In 2026, our food security is exposed to these exact same atmospheric shocks. We are looking at unprecedented levels of instability. Look at the map. This is not coincidence. This is planetary mechanics in action. A super El Niño creates a distinct drought signature. It follows the same atmospheric currents that are already suffocating the world's tropical forests. When you overlay this heat signature with global crop maps, the results are terrifying. Let's focus on the Mekong Delta. This river system feeds China, Thailand, and Vietnam before draining into the sea. It is a vital artery for billions of human beings. It is the rice bowl of Southeast Asia. Without this region, the global food math simply does not add up. During El Niño, the monsoons fail. The Mekong withers and salt water from the ocean crawls inland, poisoning the very soil we need to survive. Our sensors recorded a massive drop in delta rice yields. By 2016, this drought was visible from orbit and rice output plummeted. Now observe northern Australia. It serves as a primary planetary hub for grain and wheat exports across the globe. El Niño systematically starves the Australian continent of moisture during its most critical orbital growing cycles. The 97 event brought severe drought to the east. In 2016, we recorded similar levels of planetary damage. Regional wheat harvests can plummet 40%. This creates a systemic shock across global exchange networks because Australia is a primary wheat exporter. Scanning southern Africa now. For hundreds of millions of people below the equator, maize is the biological foundation of survival. This is not just a market commodity, it is the direct caloric fuel that these populations depend on every single day. The atmospheric shift kills the summer rains. In severe cases, we see multiple consecutive dry seasons follow this disruption. The 91 El Niño triggered a drought that brought famine conditions to 3 separate nations simultaneously. By 2016, the signal repeated. Massive crop failures forced emergency food declarations across the entire regional map at once. Look at India. The summer monsoon, a vital planetary circulatory system, is highly sensitive to these thermal shifts in the ocean. A strong El Niño disrupts the thermal gradient that drives this massive atmospheric engine, effectively weakening the monsoon rains. Our models show a delayed onset. Rainfall consistently drops below the planetary survival threshold during these years. The data shows a disproportionate impact on rain-fed farms, those lacking any significant technological or irrigation buffer. India's infrastructure provides a slight dampening effect, but it does not grant immunity from a total atmospheric collapse. In a super El Niño year, the thermal stress simply overpowers any existing irrigation technology in the worst-hit zones. Now look at Brazil's Sertão region. Small-scale farmers there depend entirely on seasonal atmospheric moisture for their very existence. Our historical records for this semi-arid zone show a centuries-long pattern of catastrophe during El Niño years. The 1877 event was lethal. Our data suggests that up to 1 million lives were lost there. Brazil has upgraded its infrastructure, yet our sensors confirm this remains one of the most climate-vulnerable zones in the Americas. A super El Niño is the specific trigger for collapse. Let us look at why this is more than just regional risk. The 2026 data suggests a synchronized failure of the planetary food grid, which is a different kind of problem entirely. Modern supply chains are efficient in equilibrium, but they are terrifyingly fragile under these abnormal atmospheric conditions. When one regional sector fails, the global market algorithm compensates, rerouting resources to fill the supply gap. Even a monsoon shortfall in India is manageable. The global system can usually absorb a single regional impact. There is enough geographic diversity in the planetary supply to mask these isolated disruptions for a limited time. But the system cannot survive multiple simultaneous failures. That is the threat a super El Niño creates for our species. It is not one total collapse. It is multiple systems underperforming, draining the global buffer from several directions at once. Our planetary grain reserves are being depleted faster than the biosphere can replenish them from the ground up. Prices are spiking. Poorer nations face starvation, not because of local failure, but because they are priced out of the global market. We have identified a structural flaw that makes 2026 far more dangerous than the crisis of '73. Modern high-yield agriculture is chemically dependent on nitrogen. It is a fragile synthetic life support system for the planet. The Haber-Bosch process currently sustains half the human population. It is our most critical planetary survival technology. 8 billion people cannot survive without synthetic nitrogen fertilizer, and the essential Haber-Bosch process runs entirely on natural gas. This creates a direct, dangerous link between the planetary energy grid and our global food supply chains. Just when planetary stress is highest, the demand for these chemical inputs reaches its absolute peak for farmers. If energy costs spike due to geopolitical friction, the entire agricultural system begins to fracture under the pressure. The cost of survival rises when farmers can least afford it. This isn't a theory, it is a documented vulnerability. We saw this signal in 2021. Energy disruptions pushed fertilizer prices to unsustainable levels for the global south. Farmers across the developing world cut back on inputs. The resulting yield drops are still being felt across multiple seasons. In 2026, our forecast shows these stress signals peaking across the entire planet at the exact same time. The geopolitical environment surrounding our energy markets is far more volatile than it was in 2021. Our supply lines are stretched thin, and the global population dependent on them has never been larger or more exposed. The 1973 crisis showed us what happens when climate stress meets an unstable system. We must watch closely. Energy shocks and resource gaps across a planet of 4 billion souls. From my perspective, the planetary mechanics of 2026, climate, heat, and energy bottlenecks, look identical. Now our biosphere supports 8 billion. Global networks are tightly coupled, efficient in orbit, but terrifyingly fragile under pressure. This agricultural data doesn't alter the carbon sink telemetry. It won't stop the forests from failing, but it follows the same atmospheric signals driven by this massive El Niño. It strikes the populations most vulnerable to planetary warming. They are all nodes on the same collapsing system. In 2026, that system faces a storm we haven't tracked in ages. Part 3. 1877. Without warning. There is a date we scientists only discuss in hushed tones, far away from cameras and public reports. We analyse it in quiet labs and research papers when trying to find the absolute edge of planetary risk. That year was 1877. We talk about it quietly because the data is concrete. The sheer scale of the anomaly sounds like alarmism, but as a scientist, I am just reading the data. I am simply reading the planetary log. The 1877 El Niño was a monster in our records. We reconstructed the sea surface temperatures from proxy sensors like ancient coral and tree rings across the globe. The data suggests an event as big as 1997. But this heat signature did not arrive alone. It hit alongside a warm Atlantic and a massive shift in the Indian Ocean's own thermal dipole system. This is the same multi-basin alignment we see in our 2026 models, ocean and atmosphere syncing up. Systems pushed in one direction at once. The result? Droughts across 4 continents. India saw its entire monsoon system collapse. The resulting drought of the 1870s killed every crop. It scorched the Deccan Plateau and Madras, reaching all the way into Rajasthan and Uttar Pradesh in a flash. China suffered total failure in its northern provinces, while Brazil's interior was hit by the Great Drought, or Grande Seca. Records show this was the most extreme drought in human history, wiping out harvest after harvest for years straight. Across Africa, the same atmospheric blocking patterns cut off rain for regions with no way to survive it. Total agricultural collapse led to the Great Victorian Famines. It was a period of catastrophic human loss on Earth. We estimate 30 to 60 million people died globally between 1876 and 1879, a planetary tragedy. That massive margin of error proves how hard it is to track death when it spans multiple hemispheres and cultures. People weren't killed by one event, but by a slow feedback loop of hunger, disease, and social decay. The human safety nets just snapped. Historian Mike Davis documented this system failure in his landmark book. Late Victorian Holocausts is a study we must examine closely if we want to survive the future. Davis argues these famines weren't just natural disasters, they were the collision of climate anomalies and broken political systems. The colonial machine was calibrated to ignore the biological reality of a starving population in crisis. Food was shipped out of starving regions in India because market mechanics were valued more than human lives themselves. Aid was delayed or restricted to keep costs low and enforce strict control over the labour force. The rail networks, built as modern infrastructure, could have transported life-saving food to those in desperate need. Instead, they funneled grain to ports for export. I see it as a climate trigger hitting a brittle system. The anomaly exposed a structure that had no protocol for survival. It was a failure of the human habitat. El Niño applied the force, and the system removed all resilience. Together, they erased millions of lives from the map. Why analyse this for 2026? Not because we expect history to repeat exactly. Our planetary tech is different now. We have the World Food Programme and international sensors monitoring the global supply. Global grain silos are massive and more accessible today than anything humanity possessed in 1877. Our orbital sensors and early warning systems can now detect a coming crop failure many months in advance. The global humanitarian grid is a real, functioning shield that didn't exist during those 19th century droughts. These are massive variables. As a scientist, I have to acknowledge how far we have come. We can't just use the Victorian famines as a cheap scare tactic. But look at the deeper question Davis asks. It is the one we face in 2026. The question isn't whether we'll face another Victorian-scale famine mortality event. As you and I analyse the modern global structure, we have to wonder about our integration. Does our obsession with efficiency create new vulnerabilities that didn't exist in 1877? We've traded colonial weaknesses for a more complex, high-stakes category of systemic fragility. The Victorian world was fragile because its systems were isolated and poorly connected. Each region existed in its own vacuum. When crops failed in India, food couldn't reach them fast enough. The logistics didn't exist, and political will favoured exports over survival. Our financial systems then weren't designed for emergency redistribution across continents. It was a failure of scale and connectivity that we can still see in the historical data today. But our modern world is fragile in a different way. We've built a highly optimised, deeply interdependent system that's incredibly tightly coupled. When one part of the machine breaks, the glitch propagates. A major crop failure in one region doesn't just stay local, it sends price shocks through the entire global market. Every import-dependent nation feels it. When energy shocks hit the fertilizer supply chain, it isn't just one country's agriculture that suffers. The costs of farming rise across multiple continents within a single growing season. As shipping bottlenecks form due to simultaneous spikes in demand, the poorest nations are outbid for cargo capacity exactly when they need food imports most. Let's look at 1973, where we saw an El Niño event collide with history. Soviet grain purchases drained American reserves overnight. The oil embargo spiked fertilizer costs, creating a crisis that the Secretary of Agriculture called the worst since World War II. And remember, that was just a moderate El Niño, a minor deviation in the climate cycle that caused a global emergency. It wasn't a super event or a multi-basin crisis. It didn't hit a degraded forest baseline or a soil moisture deficit from previous seasons. That moderate event, paired with supply chain stress, triggered an emergency for 4 billion people. The math was already getting dangerous back then. Today, we're tracking a world of 8 billion people. Our agricultural supply chains are now more integrated. They're efficient in normal times, but simultaneously exposed when the planetary system begins to shift. Energy market dependencies are even more complex and geopolitically constrained now than they were during the crisis of 1973. Now, our forecast for 2026 isn't moderate. The models suggest a super event, matching the most powerful climate shifts in our recorded history. Are we more resilient now? In terms of Victorian fragility, yes. We have early warning systems, humanitarian infrastructure, and massive productive capacity. The institutional frameworks for emergency food assistance are genuine advances that we should not overlook from a scientific perspective. But are we more fragile in other ways? Absolutely. Our systemic interconnection has created a whole new set of risks. Input dependency and supply chain optimization mean that multi-regional stress now cascades through our integrated global markets. We've engineered a system that can fail in ways the disconnected Victorian world never could have imagined. The possibility of these fragilities dominating 2026 isn't science fiction. It's an outcome currently visible on our trajectory. It's a tail risk, low probability but with very high consequences. This scenario is structurally plausible based on everything we know about global systems. When the stakes are this high, we have to name these risks and take the data seriously. Silence is not an option for us. Panic doesn't help, but preparation is the only thing that separates a managed stress event from an unmanaged total system cascade. Preparation starts by acknowledging the risk is real. 1877 is a sobering data point. It shows what happens when climate systems align against a human population that isn't ready for the convergence. We are better prepared. But is it enough? Let's talk about 3.5 to 4.0 parts per million. It's a specific, alarming number. It hasn't been confirmed yet, but our sensors will be monitoring the carbon cycle very carefully through 2026 and into 2027. This is what keeps scientists up at night. That number won't make the front page of your morning newspaper. There won't be a press conference or a viral video of a wildfire. It won't look like a flood. Instead, it will simply appear as a new entry in a dataset. It will be discussed in journals. If the worst-case scenarios are correct, it will quietly change the fundamental mathematics of our planetary survival. The number is the annual growth rate of atmospheric carbon dioxide, 3.5 to 4.0 parts per million. To understand the gravity of that range, you have to understand the history of our measurements. The Mauna Loa Observatory sits high on a Hawaiian volcano. We chose it in the 1950s for its remoteness, far from the interference of cities or thick vegetation. Up there, we can sample air that represents a true global average. It's the cleanest data we have, away from any local sources that might skew the results. We've been recording carbon dioxide levels there continuously since 1958. This data created the Keeling curve. It was named after Charles David Keeling, the scientist who first launched this vital program. It's the longest continuous record we have, and the data reveals two distinct things happening at once. We observe a seasonal oscillation. Carbon rises during the northern winter and falls in summer as vegetation grows. But riding on top of that is a steady, long-term trend driven by our emissions. From our vantage point, it's the unmistakable signature of a changing planet. That trend has climbed for 67 years without a single interruption. Let's look at what has changed over these 67 years, the rate of rise. In the 60s and 70s, we saw atmospheric carbon dioxide growing by about 1.0 to 1.2 parts per million annually. Through the 80s and 90s, it climbed toward 1.8. By the 2000s and 2010s, the rate pushed toward 2.5 parts per million. Over this last decade, excluding extreme El Niño spikes, the baseline growth has reached approximately 2.4 to 2.8 parts per million. This acceleration reflects rising global emissions, but it also signals the incremental weakening of the planet's natural carbon sinks. Both drivers are pushing the numbers higher. From our orbital perspective, those El Niño spike years stand out clearly as temporary departures from the long-term trend. In 1998, following the peak of a super El Niño, the growth rate spiked significantly above the baseline before returning to normal. By 2016, after another major event, the rate hit 3.05 parts per million, the highest reading in our recorded history. Then it dropped. The spike and recovery were both visible. The planetary system appeared to absorb the shock and reset. But in 2023 and 2024, something strange happened. Even without a super El Niño, growth rates stayed dangerously high. We recorded levels between 2.8 and 3.2, driven by record-breaking global temperatures and a devastating drought in the Amazon basin. These aren't just temporary spikes anymore. This is the new normal. The entire trend line has shifted permanently upward. Now, layer the 2026 El Niño forecast onto that already elevated baseline, a peak of over 2.0 degrees Celsius in the Pacific. Simultaneous heat stress from the Atlantic and Indian Oceans is converging. The southeastern Amazon is already operating as a net carbon source before the event. The Indonesian peatlands are structurally primed for ignition after decades of drainage and 2 previous massive fire events. Soil moisture across the broader Amazon basin has not recovered from the 2023 drought, while the Congo basin remains a total wild card. If we run the 2015 data through our current degraded conditions, an atmospheric growth rate of up to 4 parts per million becomes plausible. It's not a certainty, just a possibility. The central estimate likely sits between 3.0 and 3.5, reflecting a severe event on a failing baseline. But the upper end of that range, where multiple failure mechanisms trigger simultaneously from a much weaker starting position, is what concerns our team. We are reaching into territory never recorded in the 67-year history of the Mauna Loa dataset. Take a moment with me to process that. We have 67 years of continuous, precise planetary measurements. This spans the entire era of modern climate science, the period where humanity has been tracking the consequences of burning fossil fuels. In all that time, through every El Niño and extreme weather year, the growth rate has never reached 3.5 parts per million. A reading of 4.0 in 2027 would be genuinely unprecedented, sitting completely outside everything our observational record has shown us. And here is the part that concerns me more than the number itself. This isn't just a bad carbon budget year. It would be a diagnostic signal, a measurement telling us something specific and frightening about the state of the planetary system. Because the growth rate of atmospheric carbon isn't just an output, it's an indicator of the balance between 2 forces. How much carbon humanity is emitting versus how much the natural world is actually absorbing. If emissions stay stable while the rate spikes dramatically, that signal tells us the absorption side of the global equation has finally weakened. The carbon sink failed. Perhaps not permanently, but measurably and in ways that our instruments on the ground simply cannot ignore. For the last decade, the clean energy transition has been the central organising project for global policy. Solar deployment has been fast, wind capacity has expanded, and we have seen coal consumption in many developed economies finally decline. Electric vehicle adoption has accelerated, and battery storage costs have fallen precipitously. These are real, measurable achievements. They represent enormous investment, political effort, and genuine reductions in the rate of global carbon dioxide emissions. A reading of 4.0 in 2027 would represent the erasure of a significant fraction of those gains. Not in the sense that our green infrastructure disappears, but the carbon accounting impact of years of effort gets overwhelmed in just 12 months. It is the failure of the biological buffer that was supposed to be supporting our transition from the other side. Every solar panel installed, every coal plant retired, and every internal combustion engine replaced by an electric motor. The cumulative carbon benefit of all that work is cancelled out, and then some, by 12 months of forest and soil failure driven by climate. This isn't an argument against the transition, it's an argument for understanding what we are actually racing against. The standard framing is that we are racing against our own emissions to cut human carbon output fast enough to stay within the global budget. That framing is correct, but it's incomplete. You and I are also racing against the degradation of the natural systems that have been buying us time. They aren't fixed assets. They are a living, stressed and weakening buffer that has been quietly subsidising our climate policy timeline for decades. A 3.5 to 4.0 reading would be the clearest signal that the planetary sink is becoming unreliable. The carbon budget, the total emissions the planet can still handle before crossing 2 degrees of warming, gets revised periodically as our climate science improves. Latest estimates from the IPCC place the remaining budget at roughly 200 to 300 gigatons of carbon dioxide from 2023 onward, depending on the probability threshold we are aiming for. That sounds substantial until you note the world emits 37 gigatons annually, which means the budget vanishes in roughly 5 to 8 years at current rates. The margin is already dangerously thin. If the carbon sink weakens enough to dump an extra 1 to 2 gigatons of carbon into the atmosphere, the very scenario a 4.0 reading implies, the margin tightens even further. It is not a single-year catastrophe, but it is significant. Our current models for calculating the budget do not account for this kind of sink failure. If our models require revision, if the sink is more vulnerable and less reliable than we assumed, the policy targets built on those models must shift too. The net zero timelines, the temperature pathway projections, our assumptions about how much natural carbon absorption can be counted on to soften the impact of remaining emissions. All of it gets much tighter. You and I need to watch this critical number. Not because it signals floods or droughts, the news covers those extensively, but because of the deeper story it tells. It tells us something the headlines miss. It reveals whether the biological system that has been quietly saving us is still doing its job. Whether the invisible infrastructure of the planet's carbon cycle is holding under the greatest stress in the history of our observations. Whether the buffer remains intact. The number will appear in a data update in 2027. It will not trend on social media. It will not be the lead story, but it will effectively be one of the most significant numbers ever measured in human history. And those of us watching the data know what we hope not to see: the permanent Amazon flip. Thomas Lovejoy studied it for decades. Carlos Nobre has spent decades doing the same. These are not fringe researchers working in the shadows. They are not making claims the mainstream considers implausible. They are among the most respected and cited figures in tropical ecology. Scientists whose work has shaped the field, whose findings have informed policy at the highest levels, and whose reputations rest on decades of empirical research. When they published their 2018 paper arguing that the Amazon might be hitting a point of no return, it was no provocation. It was a warning from two experts who had spent careers earning the right to issue it. They argued the Amazon was nearing a tipping point, a threshold where the self-reinforcing feedbacks between deforestation, reduced rainfall, and forest dieback become self-sustaining, initiating a permanent transition of the world's largest rainforest into something resembling the Cerrado, the fire-adapted savanna biome that currently borders the Amazon to the south and east. Not a forest, not a carbon sink, but a different ecosystem entirely, one incapable of performing the vital functions that an intact Amazon provides our climate system. The threshold they identified is roughly 20 to 25% deforestation of the original Amazon extent. That is the level where, in their model, the moisture recycling system sustaining the interior basin fails enough to trigger a self-reinforcing transition. Below that line, the system has enough forest to maintain the rainfall recycling that keeps the interior wet enough to resist the shift. Above it, the feedback takes over. The direction of travel becomes, for all practical purposes, irreversible on any human timescale. Current cumulative deforestation of the Amazon, the total area of original forest that has been cleared or burned, or degraded since large-scale land use began, is currently between 17 and 20% total, depending on exactly how you define deforestation, which satellite data you use, and whether you include standing forest that has lost its significant ecological function. The gap between where we are and where Lovejoy and Nobre place that threshold is no comfortable margin. In some analyses, it is not a margin at all. In the southeastern Amazon, the region that aircraft sampling studies identified as already a net carbon source in normal years, the local deforestation rate is well above the average. That region has not just approached the threshold. By several measures, it has already crossed its local version of it. To understand this threshold, why the Amazon cannot simply erode indefinitely without a total systemic collapse, you and I must look at how it creates its own weather. This is not a metaphor. It is a physical process measured, modelled, and documented extensively over the last 4 decades. The Amazon rainforest transpires enormous quantities of water. The trees draw soil moisture through their roots, transport it upward, and release it as vapour through tiny pores in their leaves called stomata. A single large Amazonian tree can transpire hundreds of litres of water per day. Multiply that by 400 billion trees across the intact basin, and you get a moisture flux that is genuinely staggering. Estimates suggest the Amazon releases 7 to 8 trillion litres of water into the atmosphere every day through evapotranspiration. That moisture does not just vanish into the upper atmosphere. It condenses. It forms clouds. It falls as rain, not directly above where it evaporated, but carried westward and southward by circulation to water the forests downwind. Trees in the western and southern Amazon are essentially drinking water that was originally transpired by their counterparts to the east and north. From our orbital sensors, we see the forest watering itself. We call these massive atmospheric flows flying rivers. These atmospheric vapor streams hold more water than the actual Amazon River discharge pouring into the Atlantic Ocean. It is an invisible hydraulic engine, pumping enough moisture inland to prevent the entire rainforest from collapsing into dry savanna. This system is powered solely by the canopy. If we lose enough trees, these flying rivers simply begin to vanish. Reduced evapotranspiration leads to less recycled moisture, which cuts inland rainfall and triggers a state of permanent drought. Tree stress further kills the moisture cycle. We are witnessing a self-reinforcing feedback loop, accelerating in the wrong direction. Our models show the biosphere can absorb some deforestation, provided the remaining canopy is large enough to sustain the moisture flux. But there is a critical threshold. Once 20 to 25% is gone, the forest loses its ability to sustain itself. That specific mass is vital to keep interior rainfall high enough to support the dense vegetation we observe from orbit. If we cross that point, the feedback cycle takes control. You and I must understand how this transition actually functions. It will not look like a sudden cinematic collapse of the ecosystem. Data does not show a giant overnight die-off. We will not see a wall of fire across the continent. Instead, it starts exactly like the anomalies we see now. Sensors in the southeastern Amazon are already detecting intense droughts, higher mortality, and fires in regions that were once too wet. We see moisture-dependent trees being replaced by fire-resistant shrubs. The thermal footprint of this degradation is expanding across our maps. From our satellites, we watch the line between life and degradation creep further to the west and north every year. The decay is deceptive. On our charts, it just looks like a string of bad droughts, not a planetary catastrophe. The frightening part of threshold systems is that the shift begins long before our data confirms it is irreversible. Our satellite records will eventually flag the massive carbon release, the dying canopy, and fire zones where moisture used to rule. Changes in leaf growth timing indicate a total shift in vegetation. The data signal is faint, but the driver is clear. The interior moisture balance might reach a point of no return long before our ground sensors provide absolute, definitive proof. We may only realise the tipping point was crossed once a decade of data reveals the unmistakable path we have taken. By then, the physics of the planetary water cycle takes over. Stopping the chainsaws at that stage will not fix it. The forest would be too small to reboot the flying rivers or pull the continent back from a permanent, dry equilibrium. This is the mechanism where 2026 acts as a trigger. You and I must be precise about what that means. It is not a simple cause. The 2026 El Niño event is not the primary driver of this total dieback. The real cause is the cumulative loss of 20% of the forest and decades of damage to the moisture cycle. Global warming and the massive soil moisture deficit lingering from 2023 are the fuel for this upcoming planetary fire. That El Niño is just the final stressor that could push the entire Amazon basin across its local breaking point. It widens the transition zone, potentially pushing the total moisture loss past the point where our flying rivers can ever recover. Even if all logging stopped today, our peer-reviewed literature does not guarantee a recovery. We need to be very clear about that. This hypothesis is highly respected, though the exact tipping threshold is still an active, urgent area of our current research. Some of our models predict a higher threshold. There are arguments that the biosphere is more resilient than we currently estimate. The scientific debate is legitimate, but it is not about whether a threshold exists. We know the limit is out there. The fact that this moisture system has a tipping point is not contested. We are simply debating where that line sits. Since the southeastern sector has already failed and total deforestation is nearing 20%, the danger is becoming very real. With the 2026 El Niño looming, the uncertainty in our models is not exactly a reason for us to feel safe. The error bars on our estimates bracket the danger. We might only realise the collapse began long after the point of no return. The warning signal will grow slowly in our satellite feeds. A bit more carbon release, a slight rise in canopy temperature, more fires appearing in historically wet sectors. Each individual reading could be dismissed as just another bad year or local anomaly. The pattern takes years to prove. By the time the data is undeniable, the physical process may already be irreversible. That is how these systems function. It is why our colleagues published their warnings in 2018 instead of waiting for certainty. Absolute certainty arrives too late to act. The Amazon is just one element in a much larger, compound tipping corridor. This goes beyond rainforest carbon accounting. We are looking at a planetary crisis that is incredibly difficult to even scope. The science is solid, but the interactions between these systems are so complex that we are hesitant to make confident predictions. Ultimately, if these tipping points start interacting, the honest truth is that you and I do not fully know what happens. What we know is already enough for us to treat this question with extreme gravity. Planetary tipping points are not yet fully understood, and claiming total certainty ignores the volatile and unpredictable reality of our data. There is an intense scientific debate over what truly defines a planetary tipping element from orbit. These are subsystems that can shift abruptly into new states once an external force pushes them past a critical threshold. We still argue over where those red lines lie, how much we can trust our sensors, and how fast the transition happens once triggered. The error bars on these limits are massive, and even our most advanced climate models have known physical limitations. Experts scan the same data and reach wildly different conclusions about how close these systems are to their critical failure points. This friction is not a sign of failure. It is what happens when science operates at the outer edge of human knowledge. Yet through that noise, you and I can see a decade of research solidifying into a grim consensus found in recent reports. The evidence points towards something beyond individual elements. It argues that these systems are not functioning in total isolation. They are wired together through chemical and biological pathways. When one fails, the shock waves travel through the entire planetary machine. One failure transfers stress to the next, dragging every other system closer to its own inherent breaking point. We call this a tipping cascade, a regime in which the destabilization of one system increases the probability of every other system failing, even if the connections are indirect and the timelines vary. A 2018 paper published in the National Academy Journals by Will Stephan explored this. Rockstrom and his team introduced a haunting concept to our field: hothouse Earth. A scenario where human pressure and internal planetary feedbacks create a chain reaction that we can no longer slow down. It slides the planet into a heat trap so severe that no amount of emissions reduction could pull us back. The paper was controversial, with some critics arguing it overstated the certainty of these cascades without enough scientific qualification for the risks. Those critiques have merit. Hothouse Earth is not a direct prophecy. It is a risk framing of the outer boundaries that our coupled planetary dynamics could produce. But the core argument that these elements are wired together has only grown stronger in the scientific literature since 2018. You and I must examine the specific systems our sensors show are most relevant to the 2026 crisis. Each is under a unique level of stress, and together they reveal a larger, more alarming pattern of systemic failure. First, look at the AMOC. This massive ocean current acts as the heat conveyor belt for the entire Atlantic basin. It pulls warm surface water north from the tropics, releases that heat into the air, and returns cold, salty water to the depths. This thermal engine is why Western Europe stays temperate instead of freezing at its high northern latitude. London sits at the same latitude as Calgary, yet its climate is vastly warmer because of this constant influx of oceanic heat. The AMOC is slowing down. We see the proof in our salinity measurements and the shifting thermal fingerprints of the ocean. Between direct current monitoring and deep sediment cores, the data converges on a single fact. This current is at its weakest level in 1,000 years. The cause is fresh water pouring from melting Greenland ice into the North Atlantic, which dilutes the ocean and prevents the surface water from sinking. When the sinking stops, the current stalls, and the heat transport effectively fails. A 2021 study in Nature Climate Change analysed indirect indicators and concluded the entire circulation may be nearing a critical transition. This would be a point of no return, where it collapses into a much weaker state. That conclusion is still debated. Other researchers argue the system possesses more inherent stability, making a full collapse unlikely this century under most plausible emissions scenarios. The timing is debated, but the trend is not. Greenland is melting, and the AMOC is slowing down. The real question is how close we are to that edge. And why does this current matter for 2026? Because a stalling current shifts the entire thermal balance of the Atlantic, altering moisture and temperature over the Amazon and Africa. We have seen how a warming Atlantic amplifies the risk, making 2026 a lethal year for the world forests. By failing to move heat north, the current bottles up thermal energy in the tropics, cooking the equatorial system from the inside. It is a dark feedback loop, linking the melting ice in the north to the dying forest systems at the equator. Now, look at Greenland and West Antarctica. These are the planet's two largest continental ice reservoirs, and they are both waking up. Most focus on sea level rise, but the true threat of their instability to the global machine is far more complex. This goes beyond flooding. Our telemetry shows the Greenland ice sheet is already hemorrhaging mass at an accelerating and dangerous rate. This meltwater is the primary driver of current weakening, while West Antarctica has already crossed a threshold of committed glacial retreat. Even if we stopped warming the atmosphere now, these ice sheets would continue to dissolve for centuries. The momentum is already set. On any human timescale, this process is now utterly irreversible. Today, you and I are exploring how ice sheet loss connects to carbon sinks through the AMOC pathway. This feeds into sea level rise and the albedo effect. Less ice means less solar radiation reflected back to space. Instead, the surface absorbs that heat, putting immense pressure on every temperature-sensitive ecosystem, especially the tropical forests. I view Arctic permafrost as the clearest parallel to the tropics. It is a massive carbon reservoir, and it is failing. Those frozen Arctic soils hold an estimated 1.5 trillion tons of organic carbon, built up over thousands of years. The cold kept this carbon locked away, preventing decay. Now Arctic temperatures are rising up to 4 times the global average. In this Arctic amplification, microbes are colonizing the thawing soil. Organic carbon frozen for millennia is finally breaking down. It is venting carbon dioxide and methane into the air. Methane is an incredibly potent greenhouse gas in the short term. It is 80 times more powerful than carbon dioxide over 20 years. This permafrost feedback loop is already active. Our monitoring networks in Siberia and Alaska show thaw and carbon release rates that are far ahead of our models. The planet is not waiting for a future threshold. It is responding now, steadily raising greenhouse gas levels. This happens outside of our own fossil fuel emissions. Permafrost thaw and tropical sink failure are separate stories. They work through different mechanisms and across different regions, but make no mistake, their effects are additive. These two reservoirs are shifting from absorbers to emitters, both reacting to the same underlying warming trend. We believe 2026 will accelerate this. The Indian summer monsoon completes this picture of systemic stress. That monsoon relies on the temperature gap between the heating Asian landmass and the Indian Ocean. El Niño weakens this gap. Simultaneously, a weakening AMOC shifts sea surface temperatures across the Atlantic. These shifts break the atmospheric patterns that create the monsoon. Industrial aerosols add yet another layer of disruption. Massive biomass burning across Asia adds to the chaos. This monsoon supports the food security of over 1 billion people. If it becomes unstable, it is not just an ecological crisis, it is a primary threat to human civilization. A carbon sink failure in 2026 would sit at the very heart of these interconnected systems. It is not the biggest tipping risk, but it is the crucial thread linking our forests to the ice. It connects the oceans and the monsoons. A weak sink means atmospheric carbon dioxide accumulates much faster. Faster build-up means faster warming. That melts Greenland, weakens the AMOC, and heats the tropical Atlantic. That stresses the forests. Faster warming thaws the permafrost, releasing methane, which accelerates the warming further. Faster warming leads to more ice sheet loss, rising sea levels, and massive disruption for coastal communities. This puts more pressure on fragile human systems. None of these loops happens within a single El Niño event. This cascade will unfold over decades, which makes it incredibly difficult to communicate and far too easy to dismiss. This emergency does not arrive with one big event. It shows up as a gradual but accelerating shift. It is a shift in our baseline conditions. Once it goes far enough, the process becomes self-sustaining. No human action can fully reverse this shift. That is why carbon sink recovery is anything but a footnote. We are looking at two different planetary trajectories. One keeps enough stability for us to manage. This allows our clean energy transition to matter, ensuring our emissions cuts actually lead to reduced warming. It keeps our carbon math viable and keeps tipping points at bay long enough for us to adapt. The other path leads to systemic destabilization, where feedbacks between tipping elements drive warming even faster. It moves faster than any emissions cuts we can make. We are no longer just racing against ourselves. We are racing against the internal dynamics of the Earth. These are not equal outcomes. They are different worlds. The difference between these worlds may depend on what you and I see in the 2027 carbon data. We need to know if the systems that saved us are still capable. Part 3. The final unknown. We have been here before, twice, and both times the system recovered. In 1998, carbon dioxide growth spiked. Rains finally doused the Indonesian peat fires, and we watched the data with a mix of relief and unease. The carbon cycle bounced back. Growth rates returned to the trend line. We labelled it a severe, transient disruption. In 2016, our OCO2 satellite recorded a growth record of 3.05 parts per million. The system recovered as the Amazon regreened. The anomaly in African soil respiration faded as temperatures normalised. We felt relief, but those recoveries happened before the Indonesian peatlands were burned twice after decades of drainage. These anomalies happened when the Amazon's soil moisture reserves had not been drained by the most severe drought our orbital sensors have ever recorded. Those events occurred before the background temperatures of our major ocean basins had all reached the critical levels we are monitoring today. 2026 represents our first orbital stress test of the planetary system under conditions we have never properly validated in our predictive models. These conditions lack any historical analogue in the instrumental records. In every relevant metric, we are entering genuinely uncharted territory for our species. Today, our orbital vantage point is unparalleled. OCO2 is still transmitting, paired with next-generation satellites offering incredible spatial resolution. We have linked ground stations across the Amazon with sensors in Southeast Asia and the Congo, creating a planetary atmospheric monitoring grid. Our geostationary satellites track thermal anomalies in real time, while flux tower networks continuously stream carbon exchange data from the deep canopy below. If Earth's carbon sink fails in 2026, our data streams will reveal the catastrophe with far greater precision than we had during previous major events. The telemetry will be undeniable. The geographic signatures will be sharp. But what no sensor array can predict is exactly where the system breaks down. We do not know the threshold where the planetary ratchet effect prevents a full recovery, leaving the biosphere in a state of permanent degradation. We cannot pinpoint the exact deforestation limit where the Amazon's moisture cycle collapses, nor the specific temperature where Indonesian peatlands lose their hydrological integrity. These failures trigger regional fires regardless of the rainfall. These invisible planetary tipping points are real. Our physics tells us they exist, but they are not flagged in the landscape. We only recognize them once they have already been crossed in the data. Then the entire scientific paradigm shifts permanently. We will document the 2026 El Niño exhaustively, capturing every flood and drought from space. The drought maps will be generated. Economic damage will be quantified. At Mauna Loa, the atmospheric carbon growth rate will be measured with surgical precision. Observations from dozens of global stations will pour in. By 2027, our journals will be filled with papers dissecting what the 2026 carbon cycle data reveals. That data might show a harsh but temporary anomaly, another spike followed by a recovery, allowing us to simply recalibrate our models once again. But it could show something else. A spike that never fully retreats, leaving the global carbon growth rate at a measurably higher baseline than anything we have seen before. We might see the southeastern Amazon lose its ability to absorb carbon, or Indonesia burning hotter than 2015, despite our most advanced suppression efforts. A signal could emerge from the Congo that was absent before, a cascading failure across multiple biomes resulting in a massive net carbon release. Our instruments would reveal a weakened carbon sink that flatly contradicts every model prediction of a full recovery. If the telemetry confirms this second scenario, our entire community will be forced to confront a reality we have spent decades trying to avoid. We must face the possibility that the natural buffer, which has quietly absorbed half of human emissions for decades, is no longer the reliable planetary failsafe we have been counting on. The system won't vanish overnight, but it will be so degraded that our remaining carbon budget will shrink to almost nothing. This shift happens before we even hit the Paris Agreement limits. The window for action is much narrower than current global plans suggest. This is not a minor scientific footnote. It is a fundamental shift in the operating parameters of our entire global climate response strategy. Every carbon budget, every net zero timeline, and every international treaty depends on an assumption that the carbon sink holds. The 2026 data will either validate that hope or destroy it. We have watched this system struggle twice before, in 1997 and again in 2015. Both times, the biosphere rebounded. We updated our telemetry, learned our lessons, and moved on, assuming there would always be a next time. 2026 is unique because we are finally testing a planetary system that is being pushed to the edge. We are monitoring a biosphere under unprecedented stress. It has been strained longer and damaged more deeply than at any point since we began tracking human influence on the global climate. We are scanning for signs of resilience in the Amazon, the Indonesian peatlands, and the African rainforests, checking if Earth's lungs still function. We need to know if this buffer is robust, or if we have been spending down a diminishing planetary asset without even realizing it. Tropical forests have been absorbing our industrial errors for centuries. They are extraordinary, adaptive systems, but they are not invincible. The carbon sequestered in Borneo's peat has been stable since before the Roman Empire. These ancient Amazonian trees have been cycling carbon since long before human settlement. These biomes are not fragile enough to collapse in a single season. However, their capacity to endure is not infinite. Our data shows they simply are not recovering the way they used to. The rate at which we are testing their resilience, pushing them with extreme heat and deforestation, is higher than anything in our historical records. Current forecasts show a 61% chance of El Niño by July. Our ensemble models predict a massive temperature spike in the Niño 3.4 region. The satellites are in position. Every sensor is recording. Somewhere deep in the Amazon, the forest has been breathing harder than usual for the last 2 years. The soil is parched beyond historical norms, and the rivers are flowing at levels we have never seen from our orbital sensors. The trees are waiting for the rain. They have always found a way to survive before. That is what the data shows, and that is the hope we must monitor now. But from our vantage point, resilience is no longer something we can afford to simply take for granted.